Greetings. My name is Hector Miranda, and I will present a poster entitled Multifunctional Characterization of Biochar Obtained from Coffee Waste Pyrolysis, Structural, Electrical, and Thermal Properties. As an introduction, we can mention that the strategic use of organic waste in the development of new functional materials is a crucial component of the circular economy and the search for sustainable alternatives in the face of depleting natural resources. In this context, lignocellulosic waste, such as used coffee grounds, offer significant potential as precursors for the synthesis of biochar with advanced properties. In the present study, biochar was produced by pyrolysis of spent coffee grounds to evaluate its structural, electrical, and thermal properties for potential application in semiconductor devices. Methodology. To obtain the carbon, the coffee grounds were first prepared from local coffee beans in a coffee maker under normal operating conditions. The waste was then collected and dried at 100 degrees Celsius for 6 hours to remove excess moisture. It was then ground in a hand mill to reduce the particle size to 80 mesh. No additional treatment was applied after this, nor were any catalysts added. The diagram in Figure 1 shows the pyrolysis treatment of spent coffee grounds using a single-step argon carbonization method. The waste is placed on a stainless steel plate, then placed inside a quartz tube, and the quartz tube is then placed inside a horizontal tubular furnace. A gas flow of 30 milliliters per minute is applied, and temperatures are reached at 700, 800, and 900 degrees Celsius for 60 minutes. Results. Among the analyses performed, I show that images of the carbons were obtained with an optical microscope at 100x magnification. Micrographs of carbon obtained at 700 degrees Celsius showed irregular granular particles with somewhat rough surfaces, but the samples did not exhibit high porosity. However, a change in the morphology of the carbon can be observed in Figure B. The heat treatment resulted in the formation of large, irregular lumps on the surface of the carbon. This could be due to the evaporation of volatile compounds from the surface of the coffee beans. As shown in Figure C, which corresponds to the carbon obtained at 900 degrees Celsius, it has a more porous structure, indicating that the heat treatment temperature has a pronounced effect on the generation of porosity due to the evaporation of volatile compounds, resulting in an increase in surface area. Therefore, as part of a composite, it would facilitate interaction with a polymer matrix. Figure 2 shows the X-ray diffraction analysis of the carbon samples. Spectrum presents the typical structure of disordered carbon materials, with a broad curve appearing. However, in spectra B and C, the peak near 25 degrees narrows with increasing temperature, indicating a change in the crystal lattice size and the presence of turbostratic carbon with a tendency to form small graphitic structures. To characterize the carbon's functional groups, the FTI/IR spectra were analyzed, as shown in Figure 3. This spectrum shows a very faint broad band located approximately 3,400 centimeters, attributed to the OH hydroxyl groups. Its low intensity may be due to the low humidity and adsorbed water present in the samples. The band at 1741 is attributed to the carbonyl oxygen groups. A small peak is shown near 1550 due to the presence of saturated and unsaturated carbon-hydrogen structures. At 1370, saturated carbon is observed, and at 1243, carbono-oxygen is observed. In the region from 1148 to 1030, bands appear that can be identified as a lignocellulose-derived matrix with the presence of polysaccharides and aromatics. In general, the carbons show functional groups characteristic of a lignocellulosic matrix in their bands, but with a lower intensity, reflecting a significant loss of mass in the pyrolysis process, reducing the variety of structures present in the carbon particles. However, carbons obtained at temperatures of 700, 800, and 900 degrees Celsius also retain inorganic material within the carbon microstructures, forming an important component in the porous carbon matrix. In conclusion, it can be said that carbon produced from spent coffee beans can have a high surface area and porosity, which gives it useful properties for various applications, in addition to being a simple and economical process. The properties of the resulting biochar are significantly influenced by the pyrolysis temperature, as is the case of porosity, which occurs with increasing temperature up to 900 degrees Celsius, which is the optimum temperature within the experimental range. Temperatures tested for the preparation of better carbons from spent coffee. This additional porosity in the carbon could improve its interaction with polymeric materials, resulting in better adhesion between the carbon and the polymer matrix for the creation of new composites. Furthermore, these pyrolysis temperatures induced a change in crystallinity in the carbon structure, observed through X-ray diffraction curves, which could confer properties as an electrical semiconductor in a dissipative anti-static packaging material. Thank you for your attention. I look forward to your questions.